line. All right, so we know that the shortest distance between a point and a line would be in a perpendicular relationship. All right, so it would be the line segment that forms a right angle with the line in question. All right, so we know how to establish whether or not two segments are perpendicular or orthogonal if we know the dot product between the vectors that make up those two paths. Then we can find the dot product. We'll see that it's equal to 0, guaranteeing that there's a right angle. But that seems like a lot of work. Maybe there's a better way, and this is the better way, and it's a clever better way, because you may or may not remember this. This part of the formula is also the area of a parallelogram. All right, the significance of that is, it'll become obvious in a second. All right, so before I get into the nuts and bolts of this, let's draw a quick sketch. All right, I'm going to draw, optimizing memory usage. Please wait. Okay, I've waited long enough. All right, so let's say I have just some vector in space. Say it's shooting out over here. Actually, you know, I was going to make it probably more complicated than I need to. Well, let me start off with a simple case, and then I'll show you the more elaborate case. All right, so this is the ideal situation. The point in space that you're looking to find the distance of is perfectly, if you were to connect it with a line segment, perpendicular to the given line. If that's the case, then what you would be doing, I'll just attempt to draw a little line segment here. You could have your vector going in either direction, but in theory, if we're talking about a vector intersecting another line, you would think that that vector would be traveling in the direction of the line. But in reality, it really doesn't matter. But I'll draw it this way. And then you would also have some other vector, and I'll just pin it at this location and shoot it off here. All right. So regardless, and you'll see in a second why it doesn't matter which way we draw the two vectors. If I want to create a parallelogram out of this, I can do it this way. Or I can transpose or translate the vector down below the line and draw the parallelogram on the other side. But it would be the same exact parallelogram, which is why it doesn't matter where you draw or which direction you draw the vector. All right, so if I were to find the cross product between PM and vector V, and find the magnitude of that, that would give us, I'll just write equals, the area of the parallelogram. Now, this vector V, I'll try to highlight, well, I'll just leave it black. That vector V would be the length of the base. Its magnitude anyway. All right, so just going back to the definition of the area of a parallelogram. It would be base times height, right? So if I were looking for the length of, let's say, the height, just simple algebra, so no vector operations here, I could just take the area of the parallelogram and divide it by whatever the length of the base is. All right, and so the height would be equal to the area of the parallelogram divided by the base. Now, if I tell you that the area of the parallelogram is the cross product between PM and V, and the base is the magnitude of V, then that operation would give us the length of the height. All right. Significant drawback to this approach, seeming drawback, would be, okay, well, what if they're not right angles? All right. So that's where my more elaborate diagram was going to come into play. So let's say I have, yeah, I'll just do it the way I was going to do it before. Just kind of shoot it out here a little bit. Too long. Something like this. All right, so let's say you had something along these lines where you have a point, let's say just floating over here, that we call M. So I'm moving my M. It's basically, I just don't want to draw an entirely new diagram. I'm making my new M be this point over here. All right, so just kind of play this out logically. If I were to just follow the same operations, all right, so considering the operation here, I have a vector PM, a vector V. I find the cross product. That would give me the area of this parallelogram, right? All well and good. If I were to divide it by the length of the base, which would be the magnitude of vector V, that would give me the length of this side. Still fine, it's an operation. That would give me the length of the height, right? That if I were to divide the two, just following all these calculations, it would give me the length of the height, right? Which would be, based on this diagram, this side here. All right, so that would be the height. All right, but since all I'm looking for is a distance, that height would correspond to this distance, which is essentially what I'm looking for. All right, so these two distances would be congruent, right, because the height it just represents the distance between bases in a parallelogram. So whether it's the base extended or whether it's contained within the figure, it really doesn't make a difference. It kind of goes back, all the way back, to finding the height, for example, of an obtuse triangle. So how would you do that if it was an obtuse triangle, which would look something like this, and you needed to find the height? You'd drop an altitude on the outside of it and extend your base and then find this distance. This would be the height, right? So it's the same idea, all right? So now consider the situation. Let's say a question asked me to find the height of an obtuse triangle, right? And I was given vectors. Well, the same operations would carry over, because that obtuse triangle, any triangle, is half of a parallelogram. So all I would have to do is at least visualize what the entire triangle would look like, find the cross product between the two vectors that make up the legs, and then divide by the vector, the magnitude of the vector that represents the base. And that would give me the height of the triangle. All right, so this is not just find the distance between a point and a line. This could expand to other concepts as well. All right, so it's kind of a nice little feature. There's other ways to do it, and it's very procedural. I don't really care for the other ways to do it, only because, I mean, this way is procedural too. You still got to find the cross product, and you still got to find magnitudes and things like that. But this is a more malleable approach.
Yeah, I was going to ask, would you be able to use the distance formula to find the height, since you said they're congruent together?
So you could, as long as you have another point. right? So if you have 2 points available, so if I knew what this point was, then I would be fine. The problem is I'm not always going to know what that point is. If I have the equation of a line and a point in space, if I wanted to use the distance formula, I would have to find the point on the line that's closest to the point that's in space. All right, and in order to do that, we would have to have a vector valued function that represents Pm and find the dot product between that and vector v, showing that that's equal to 0 and solve that equation. It's another way to do it. It's a good enough way to do it, but I like this approach much better.
It would just be too complicated.
Yeah, it's just a lot of algebra all over the place, and it's fine. It gets the job done, but this way is very flexible. And so the problem that we had here, find the distance between point 036 and the line with parametric equations given. All right, so if you want to draw a diagram, it's probably not a bad way to go. What would the diagram look like? Well, you're not going to plot it point by point. So good thing about these kind of problems is all the diagrams look the same. So you have 1 minus t, 1 plus 2t, and 5 plus 3t. And we learned last class that corresponds to some parallel vector v, which would have components of -1, 2, and 3. All right, because remember, we don't call it slope in 3 space. We have something called a gradient that we'll talk about when we get to actual surfaces. But in terms of the path of a line, we don't describe it with a slope, but we do describe it with a direction. That direction would follow a particular vector, right? So the vector that it follows is -1, 2, 3, or multiples of that, right? This one will be pinned down at the coordinates 1, 1, 5, all right? So with the starting value, so there's a point on the line equal to 1, 1, 5. We also have the point in space of 0, 3, 6. All right, so I'm looking for PM cross V. All right, well, we got a V, I just need PM. All right, so P is the point in space, M is a point on the line. I don't know where that point is. I'll put it anywhere I want, I guess. So I'll put it right here. Call it point M. M for point. So the vector P to M. All right, so 1, -2, -1. That's a poor quality -1. Just got to shoot it over here. It's just checking my simple arithmetic. 1 minus 0, 1 minus 3, 5 minus 6. All right, well, I double checked it, so if I'm wrong, it's definitely on me now. All right, so we're going to find the cross between P, M, and V. And the magnitude of that, but first the cross. All right, so notation-wise, and let me just bring it in a little bit and clean it up. IJK, P is 1, -2, -1. PM is 1, -2, -1. V is -1, 2, 3. All right, so we need the I, coefficient of I, which is the determinant of the entries in the J and K columns. So -6 minus -2. All right, so -6 plus 2 would be -4.
Professor? Where did our vector PM come from again?
That's the, I'll bring it back over here a little bit. The difference between the points M and P.
Oh, okay.
So 1 minus, and so on.
Thank you.
No problem. So -6, and in all honesty, aside from complete conceptual misunderstandings, which often lead to disasters, the most common error I see in this particular unit is people messing up the basic arithmetic for the cross product. Right? So it happens to me all the time. Keep an eye on me, and obviously I'll keep an eye on you.
Yeah, you're always going to be subtracting, right?
You're always going to be subtracting, but then you're subtracting negatives. But you know what really screws people up the most is
J.
not even that. It's the zero entries. Yeah, because you're supposed to multiply by 0. You know it's supposed to become a 0 when you multiply, but for some reason, like every day of the week, 1 times 0 is 0, except that day you're taking a test, at which point 1 times 0 for some reason becomes a 1. I have no idea why. Right? So it's and really only related to the cross product for some reason. I have no idea why. So for the J, 4, and this is going to become positive. So 4 minus, you see I did it, look. I did it right there. I said 4. It's only with the cross product this happens. So 3 minus a positive 1. All right, so 3 minus 1 is 2. So, but it's negative because it's a J term.
Wait, why is it negative?
It's a J term.
Wait, I thought it was I plus J minus
No, it's always minus J.
I minus J plus K.
Minus J plus K.
Oh.
And then 2, and then we'll also have a 2, right? So 2 minus 2, 0. All right, so feel free to write the 0K. I'll write it.
Okay.
I make jokes for my own benefit sometimes.
Take the magnitude.
We're going to take the magnitude of that. So I need, do that in purple. So the square root of 16 plus 4 plus 0 if you want, square root of 20. And I need magnitude of V, square root of 1 plus 4 plus 9 is equal to root 14. Yeah.
Shouldn't it be positive 2?
It could be. Let's take a look.
Positive 2J?
Right.
So both the ones are,
So these will become positive, so it's going to be full up. I did it again. Okay.
You said it, now you're doing it.
So 3 minus 1.
3 minus 1 is 2, right, but then the
It's
negative is
minus
built
J.
into the formula.
Okay.
All right, so the area, area is the root of all of this, but the distance, which is the square root of 20 over the square root of 14, which, I mean, we can clean it up a little bit. It's 2 root 5 on top, but that doesn't really do anything, right? So big square root of 10/7. Good enough? I mean, I can do a quick calculation on that somewhere. I just haven't taken my calculator out yet. Just to see decimal-wise what that would be.
1.19.
1.19?
Yeah.
Approximately. Of 1. All right. Yeah, very specific about it. Equation for a plane in 3D, right? Because you could be looking at a plane in 2 dimensions, but you're only going to look at one plane at a time. Specifically, we want to know what a 2-dimensional plane would look like floating around in 3 dimensions. All right. So, how do we do that? Well, this is the key ingredient. N times vector PQ equals 0. But it's like, okay, cool, that's another rule. Where did that come from? I'll read the little preamble here. Find the equation of a plane P that contains a given point, right? So you've been told this point in a problem on the test, whatever, and that is perpendicular to a given vector, right? So that's the key term there, perpendicular. Highlight worthy. Let me get a good highlight color, bring it over, and highlight. It's already bold, but let me highlight it. All right, it looks gloriously highlighted on my screen. It just, I mean, it's beautiful. I can't even like, it's just so beautiful on my screen. All right, so I need it to be beautiful on yours too.
Beautiful.
Yeah, it's just, now it's just it's something else. Otherworldly is how we would categorize that. I have it in ninja mode, so I gotta change that. All right, use the displacement vector between a given point P and an arbitrary point Q, x, y, z. So kind of like how we were defining our parametric equation of a line. It must be perpendicular to A, which means their dot product has to be equal to 0. All right, so you could define the orientation of lines and planes not only by the direction that they're going, but the direction that they're not going. All right, so sometimes telling what's not happening is just as good as telling what is happening. Right? So in this case, we're not telling what the direction is of the plane. We're telling what the direction is of the vectors that are perpendicular to the plane. Right? We have infinitely many vectors that are perpendicular to a given plane, if you have a single plane. But they all have to be parallel to one another. Right? So if you know one of those vectors, you really know them all, because any one vector has to be a scalar multiple of any other vector. Right? So if you know one, then you know everything there is to know about the plane. Right? So that's where vector n is going to come from. Why is it n? Well, just to be as complicated as possible, really. It's for the purpose of confusing you. No, that's not true. It's not p because we seem to be using p for everything else. This actually stands for normal vector. All right, so a normal line, if you think back to Calc 1, perpendicular to a tangent line. All right, so, and why that's called normal, I don't know. I think at that point it was to confuse you. But a normal line is a perpendicular line to some other given line. In the case of Calc 1, it's perpendicular to a tangent line. Here, it's perpendicular to a plane. All right, so
Both sides, like from up and down?
Say it again?
One side. This is like if all the vectors are on the top, then we're kind of missing one.
Oh, it would account for the bottom also, because if you have a vector if you're defining all vectors that are perpendicular as being scalar multiples of one another, one of the scalars could be a negative, so that would change the direction of it. So it allows for it to go upwards or downwards. All right, PQ is the displacement vector between x, y, z, so your variable coordinates, and the given coordinate that you have. Right? So you need to know something about a point that's on the plane, but that kind of makes sense, because how are you going to define, how would you define the equation of a line if you didn't know a point on the line? So how would you define the equation of a plane if you didn't know something about the plane? Right? It's good to know the normal vector, but if you know the normal vector, you probably know where it's pinned. Right? That location where it's pinned would be your given point. Right? So let's actually work this through in general terms, which means proof, which means, hey, this could be on the test. But now you know enough to take this stuff seriously. Like, oh, he wasn't kidding. It will be on the test. And it's like, oh, that's good to know. I mean, he said it the first time around, but we didn't believe him. Then he told us on the breakdown for the test that it was going to be on the test, and we still didn't believe him.
So I did that last question wrong?
No, lots of people got it right. It's one of those things where you want it to be the case that everybody got it wrong, because then it's like, oh, throw that question out, free 5 points for everyone. But unfortunately,
That was actually the easy proof. Yeah, right?
yeah. As proofs go, that could have been a lot worse. Last year's version of it was the arc length of a parametric equation. Yeah, that's the one where it's like, I know I could do the steps to get there, but it's going to take like half the test time to do it. Yeah, so then I ran into that problem. So out the door went that one. So P to Q, x minus x sub O. Y minus y sub O. And z minus z sub O. That dot product should be equal to 0. All right. Dot product just means multiply corresponding parts. A times x minus x sub O. It's a scalar multiple, so or scalar product, so I could use ordinary parentheses. Plus b times y minus y sub O. Plus c times z minus z sub O. All right, I gotta check my phone. My son's game should be over by now. I left, he had a hockey game. I left right at the end of the second period. So in his league, you once you get a hat trick, you can't score anymore. So he scored a fourth goal, and my wife's upset. She's like, "Ugh, he scored a fourth goal, but it didn't count." I'm like, "Yeah, that's because you can't score anymore after that."
Basketball, they'll make kids sit. They score too much. And
Oh.
They can't play the game, which is the worst thing. When I used to ref games, I would tell kids like,
You can't play anymore because you're too
don't
good.
Stop scoring. You score one more time. You can't play for the rest of the game.
Ugh.
And they're like 5 minutes in, 20-minute game.
That's rough. And you cut it into playing time. At least in hockey, they just make them play defense.
Okay.
The problem is
That
he
breakaway
gets
is
the
gone.
puck and he's like, "See ya," and he takes it all the way. So he's a good player. I'm extra proud because I can't even stand up on ice skates. But an expert skier, which has a lot of the same characteristics, I don't know. I should be awesome at both. I don't know, but I'm like, I don't even get like 2 feet away from the boards before I think, all right, I'm out of here. So look at all this stuff. How are we going to get an equation out of this? Well, if you look at all the details here, really, I mean, if you think back to how you write the equation of a line, x and y is important, right? We got to keep those as variables. Everything else is constant, right? In the equation of a plane, all right, well, it's x and y, but also z. So any term that has an x, a y, and a z, we want to keep together. And everything else we want to get rid of. Not get rid of, but let's shoot it over to the other side of the equation. All right, so these folks are going to go over to the right-hand side and become ax sub O plus by sub O plus cz sub O. Now that's a hideous-looking equation, but what they do, wherever they are, they define D as equal to ax sub O plus by sub O plus cz sub O. And so we end up with ax plus by plus cz equals D. You can understand why they chose D. It just kind of has a nicer flow. We know it's not a variable. We know it has to be some constant. And we've used A, B, and C, so we're not going to throw in an alpha. We'll just follow the trend and use a D. All right, so this is the equation of a plane in general form. And so what it tells us is that you pretty much have most of what you need when you're looking to write the equation of a plane, just by knowing the normal vector, because the normal vector is ABC. You already have the left-hand side of the equation just by knowing that one piece of information. Everything else that you're going to do is simply to find the d value. But if you really think about it, look at the structure of the d value. It's a times x sub o, b times y sub o, and c times z sub o. It's not exactly a dot product, because if we're thinking of x sub o, y sub o, z sub o as a coordinate, an ordered triple, then you don't dot product, you don't dot a vector against a coordinate. But you can easily create a vector from a single point, right? So what D could be thought of is, a little consequence here, is that D is equal to the dot product of ABC and the vector that has components of x sub o, y sub o, z sub o. So you have, instead of doing all this algebra, because this algebra was just a proof to get us to the standard form of a plane, once you know the general structure, if you know the normal vector, you find the dot product between that and the vector whose components are your given point, then you have your d value, and that's all you need. All right? I'm going to throw this over here. I know it's not recycling. I got spoken to by a student one time for that. It was fall 2015. This classroom, walked over there casually in the middle of a lesson, dropped it in there. Student looked at me and said, "Really? You're not going to throw that in a recycling bin?" At which point I fished it out, walked out into the hall, and put it back in the recycling bin. I felt guilty as all hell. I got over it, though. 4 years. It took a long time, but I got over it. Yeah.
You're not bitter about it.
I'm not bitter, not bitter. She was a great student, though, so, and a very, very nice person, obviously civically conscious, too. So the equation of the plane containing the point 221, right? So that sounds like a point on the plane, specifically because it basically said it's a point on the plane. That's perpendicular to the vector 336.
That's still in the proof?
Sorry?
That's in the proof, right? D is ABC.
Yes.
That would be part of the proof, yeah. So 336 would be our ABC. So what I would need to get D, now, again, there's only so many letters in the alphabet. So D a few minutes ago meant distance, but now it just means an arbitrary constant that's used to define the equation of a plane. But it doesn't mean distance. So, yeah.
Favorite letter?
Yeah, I mean, I didn't invent this stuff. I'm just really good at it, yeah. All right, so I find the dot product of these two vectors, all right, the given perpendicular vector, and also the vector whose components are the given point, all right? And so that would be the vector from the zero vector, all right? So 3 times 2 is 6, plus 6, plus, oh, well, I don't remember that being so cool, but all right, I'll take it. And so we're looking at 3x plus 3y plus 6z equals 18. That's the plane. And you can verify it pretty easily. All you need to do is make sure that any point that you claim is on this plane would satisfy this equation. All right, so plug in a 2, 2, and a 1 and see if it works. It does. I mean, well, it does because we did all the calculations to get us here. but also, I mean, 6 plus 6 plus 6 is equal to 18. That's beautiful. And we could check it on Geogebra in a second just to see what it would look like. Now, we do have to sketch the plane. Now, this is one of those issues that comes from the idea of trying to sketch on 2 dimensions something that exists in 3 dimensions. So it's never going to look quite right. Right? So, but what we're going to do is find intercepts, right? Because if there are, assuming it's not parallel to a particular plane, you know, the XY plane, the YZ plane, or the XZ plane, it should go through at some point, maybe not at convenient locations, but it should go through all 3 axes, right? So what I would do is let x equal 0, in which case, actually, sorry, I meant to say 2 variables, x and y equal 0, right? Because if we're looking for the z-intercept, I would want to zero out both x and y, right? So 3 times 0 plus 3 times 0 plus 6z equals 18, which would give you 6z equal to 18, which means z is equal to 3, right? All right, so we're zeroing out the x's and y's and determining what that would mean in terms of z. All right, so that gives us a z-intercept of 3. Right? And, you know, just kind of visualize that out, or at least count the boxes in your mind. You say, okay, well, in order for this to be true, I'm standing at the origin. I'm not taking any steps outward towards x. I'm not taking any steps to the right towards y. So I'm still at the origin. The only thing I'm going to do is take 3 steps up in the direction of z. All right? So that would be my z-intercept. I'd do the same thing for the other 2.
So what does that 18 mean? Like what 18, what does that mean?
It's just a constant.
Oh.
Yeah, it's a constant that satisfies the equation, but aside from that, nothing, I mean, overly meaningful. I mean, it's a perpendicular or orthogonal relationship between your perpendicular vector and the given point. So it establishes orientation, but aside from that, like, the quality of the number doesn't really have any significance. Now, in this problem, it's great that it's 18 because the numbers work out nicely. But that's not always going to be the case. I'll let x equal 0 and z equal 0. In which case, you know, just to cut to the chase here, that means in my plane equation, x and z are going to zero out, in which case the only thing that's going to remain is y. So 3y is equal to 18, and so y would be equal to 6. And so would x, right?
So does that mean that the plane crosses all 4 points?
Yeah. So
It's like a nice little, it's like a curved, weird plane.
yeah, it's going to be kind of on a slant. I already kept x. So, and if y equals 0 and z equals 0, then x would be equal also to 6. Same calculation, so there's no point in doing that again. All right, so let's see if I remember to fix the number of points that I have on my graph. Because, oh, look at that.
Exactly.
All right, so to draw the sketch, you can't draw a plane going off in infinite directions. Infinite directions for infinite distance. I mean, what would that look like? Start shading your entire piece of paper. You're like, I drew the plane, you know. Like, yeah, okay, full credit, because technically you're right.
When's the next test?
Connect the dots and shade it in. I had a triangular piece of cardboard that I used to bring to class, I almost always brought it into class on the wrong day, which is why I don't have it anymore, because I brought it one time and I forgot it. But yeah, so what I would do, so you'll just have to imagine this. Go into the corner, take my triangular piece of cardboard, and just lay it down in the corner here. Not flat on the surface, but on a slant, so that it's pitched on an angle, leaning the point into the corner here in the crevice, and then flat out along the wall and creating a triangular path. And so that was my visual to describe what this was supposed to look like. I think it looks like a great diagram, but that's only because I know what it's supposed to look like. So, yeah, it may look like nonsensical scribble to you, but it's supposed to be like what I described over there. Right? In terms of the graph on Geogebra, because you don't have to experience what I experienced in school. You can actually see a quality diagram. I'll shift it over here once I actually type it in. Yeah, so you don't have to take your teacher's word for it anymore. You can actually see it for yourself. Although that doesn't look anything like the picture I just drew. But that's because the picture I drew is the best you can do. What do we got? Movie fights. I'll have to check that out later. That doesn't. The screen is garbage. Something a little bit more soothing. Oh, that's too soothing. Put you right to sleep. Exactly. All right, well, that's probably as good as it's going to be. All right, so this is really what we're up against here. You know, the plane has infinite distance, but you can see that it's crossing, it looks like 3 over here. Looks like a 6. And then over here, actually, it's a little easier to see because the points are a little faded where it's on the other side of the plane, and then it starts getting a little darker when it's on the near side. But you can also manipulate the orientation and see what it's supposed to look like, because it's supposed to go off in infinite distances, in infinite directions. So, and then, you know, spin it, let it go. Because that's something it can do, and it's fun to let it do that sometimes. Do that. Doesn't really mean as much, but it's fun. Not as fun on the phone, though, because I don't know why. It's just not, we're not there yet. There. Almost there, though. All right, so I'm going to put a star on number 7 because this one's giving you points, but I'd like you to try to figure this one out first before I spoil the fun for you. It doesn't seem like it would follow the same kind of approach that we took, but really if you're thinking about the idea that we need something perpendicular to the plane that all of these 3 points are on, then you start kind of hopefully thinking along the lines of cross product, right? Because if you know the definition of cross product as, you know, it generates a vector that's perpendicular to 2 given vectors, then it seems like it's precisely what we need. Right? So if you create 2 vectors out of this and find the cross product, you'll get your normal vector, and then all you need is a point on the plane. Any one of these 3 would suffice, and off you go. All right, so cross product galore here. Intersection of planes. This could be easy, or it could be pretty challenging. It depends on the way the question is phrased. So 2 planes in 3 dimensions are either parallel or they intersect in a straight line. All right, so they're parallel or they're not. So the relationship that exists for lines in 2 space does not apply to lines in 3-space, because you could have skew lines, lines that they don't intersect and they're not parallel to one another. But the relationship for lines in 2-space does transfer over to planes in 3-space. Right? So that idea of they're either parallel or they're not, that is true for planes in 3-space. All right? So the question would become, well, all right, in what way would they intersect if they do intersect? Right? They could have a perpendicular relationship, or they could just be at a slant, or maybe they're parallel completely. The good thing about it is if you can make a determination of the relationship between the normal vectors, then you'll have an idea of what the relationship is between the planes, right? Because my enemy of my enemy is my friend. It's that idea. If you're talking about the normal vectors being perpendicular to one another, right, the planes that originate those normal vectors must also be perpendicular to one another, right? So if the normal vectors are parallel to one another, then the planes themselves must be parallel to one another, right? So it's funny. So this is the easiest analogy, the pen between the fingers, but I can't not, like, I have a disturbed mind, I guess. It's like a nail right through the hand. There's my normal vector, so, but this is obviously the safer way to go. Right? So if you have a pen in one hand and a pen in the other, you can easily see the relationship. Right? So they're both parallel to one another, so the planes would be parallel to one another. All right? They're perpendicular to one another, the planes are going to be perpendicular to one another. All right? And just imagine that being a bloody mess with nails, and you'll yeah, so you can, Halloween costume ideas, you have one right there. You can be perpendicular planes, so just like with fake blood, not terrifying.
Call the chainsaw vector.
Yeah, Texas chainsaw vector. Yeah. All right, so that's what all this is addressing. Right? So we want to find the equation of a plane containing the point 314 that is parallel to the plane to, well, I was going to just name off the perpendicular vector 211, but that's really the key to understanding how to handle something like this. So if I know that the normal vector is going to be 211, and it's going to be parallel, so this point is not living in this plane, but it's a point that's parallel to that plane, which means that the normal vectors would be scalar multiples of one another. All right, so I can invent a new normal vector if I want, double it, triple it, multiply it by -1, -1/2, doesn't make a difference, or I could just use that, right? Because the direction of it would have to be the same. All right, so this would be my x sub o, y sub o, z sub o. Now these points would not satisfy this equation. And if I plug in a 314 here, I'm not going to get 1 as a result. So what I need is a new d value to represent the plane that is parallel to this. All right, so my new plane is going to be 2x plus y plus z equals something other than 1. All right, so I'm going to find the dot product between n and x. Well, I'll just actually write it. I was going to use notation, but 2, 1, 1 and 3, 1, 4. It's going to give us 6 plus 1 plus 4 equals 11. And so therefore, we're looking at a plane 2x plus y plus z equals 11. All right. Now, personally, I don't know. You might feel differently about this. It's not. This is by no means a requirement, but I am pushing this GeoGebra stuff through the tech assignments. So you may think, well, I'll just do the GeoGebra to satisfy his weird need to have us use that software, just for tech assignment purposes, but I'm never going to use it for anything other than that. That's fine. But I would like to know that I just did this correctly. So I put 2 planes in, make sure I type it in correctly in theory. All right, I did not because my planes don't look right. I'll get it up on the screen in a sec. I just want to make sure I have it in here correctly before I give it to you. I accidentally typed in 2x plus y plus x again. It was weird. It's a weird mistake to make. All right, so here we go. Got my 2 planes, the original, the extra crispy, and you put a little sphere in there and you have a TIE fighter. Yeah. This looks like the targeting scanners on the Millennium Falcon. All right, so, okay, cool. We know it's parallel, but we knew that before we tried figuring out the 11. All right, well, how do I really know it's right? Well, let me put the point that's supposed to be on my new plane. 3, 1, 4. That does appear to be on my new plane. All right, maybe you're not sure that that's the new plane, so let me shut off the one that was the old plane. All right, my new plane does contain the given point. I did it right. It's not even like I'm pretty sure I did it right. I did it right. They're parallel to one another, and the given point is on the plane that I wanted it to be on. All right, so Geogebra is a really good resource to make sure you got a good handle on this stuff.
How is it that you said that at one point you feel like Geogebra would be available during a test? How would you do that?
They have a test feature.
But then you would have a computer with you, or a tablet, or a phone?
Yeah, so the student would have to have a tablet that has the Geogebra app on it. Then you would enable the testing feature on it. That locks you out of every other feature on the tablet, except for the functions on Geogebra that I'm willing to allow, which is most of them. And then it has a set screen. So like the border on this one is blue. It would turn to green or red, I can't remember, but a different color than blue. That lets me know that you're in test mode. If I set it up with, I think it's Apple Classroom, then I could actually see your screens on my laptop. And then after all that's over, let's say you figure out like, okay, that's cool. He didn't come around and look. He's not looking at his laptop. I could totally cheat. At the end, once you disable the testing feature, it tells you, or it tells me, the amount of uninterrupted time for which you were in the test mode. So if the test started at 6 o'clock and ended at 8 o'clock, and it says that you were only in uninterrupted test mode for 15 minutes, I'd make you sign a waiver beforehand that says that if anything like that happens, you're getting a 0, but that would mean that you were out of the testing mode, in which case you had access to the internet. And which, well, that's the reason why we don't do it already. Yeah, because I can't guarantee that yet.
But then we would be able to do something like this, where we could verify, oh, this is actually parallel.
Exactly.
I know I got this right.
Yeah, I mean, we're almost there. We're not there yet, but we're almost there. Like I think we're maybe like probably a year and a half away. So I don't know. I'd like to see it happen sooner rather than later, but
That doesn't help us very much.
I know. I know. But when you think about the fact that I had to learn all this crap without Google and stuff, and YouTube, and
GeoGebra.
and TI-83s,
I had those.
I didn't even have that. So put that in perspective. Like we had, when I was starting out, it was TI-81s and then TI-85s, and then after that it was TI-83s. But half of the functionality was either not created on the TI-85 or none of my teachers knew how to use it, so they couldn't teach us how to use it. So it was like it didn't exist anyway. So I had nothing except for my wits and my will to survive. So anyway, process for finding intersection of planes, because that's not too bad. You know, you're given a point, you know that the parallel vector, the normal vector is going to be parallel, so you know you can use the same vector. That's great. But what happens if they're going to intersect? You have to find the parametric equation of the line that represents the intersection between those two planes. Because if you imagine, and I can help you imagine in a few minutes, two planes intersecting, the path that's generated by that intersection will be a line. And we've already covered the fact that the only way you're going to represent a line in space is with parametric equations. So this technique is going to help us do that. All right, so it's elimination. Eliminate one variable from the two equations and solve the remaining equation for one of its variables in terms of the other, blah, 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 blah. All right, I'm going to show you a better way than that, though. So, linear algebra, our best friend when it comes to stuff like this. Because we can, if we want, solve by eliminating a variable. It looks like z would be a nice variable to eliminate here. You know, you subtract the two equations from each other, z would go away. So z would be your independent parameter, and from there you can figure out everything else. But let's not do it that way. All right, let us write a coefficient matrix 2, 1, 1, 1, 3, -5, 1, 4. And we're going to row reduce that. Put that in reduced row echelon form. R ref. All right, so to the calculus, to the Hindenpeter. Again, it's the linear algebra stuff is not me tooting my own horn or anything. It's like, oh, cool, I know linear algebra. It's not that. It's supposed to be a gift for you. It's supposed to help you not have to do the mundane algebra that would take you minutes to do. All right, and I don't mean minutes like 1 or 2 minutes. I mean minutes like 10 or 15 minutes. All right, so in this case, it's not too bad, but sometimes it can get pretty out of hand. So the linear algebra just keeps you from getting bogged down in that. And also, I mean, you know how it is. You do the simple algebra, and you make the simple mistake in the simple algebra, and then you spend the next 10 minutes trying to figure out what the hell you did wrong. So this is going to help alleviate that. So you want to become very familiar with this because it is a time saver, and you know there's I don't even know. It's supposed to be a gift for you.
It's not viewable.
What's that?
It's not viewable, or at least not all the way through.
No.
Like I can't.
Hit that.
I accidentally got.
Isn't it 2x4?
Yeah, I got distracted.
It's
And
2x4.
I was in motivational speech mode.
Thank you, buddy.
Yeah, we know we got storytelling mode, we got joke mode, we got the this'll serve you well, listen to me, I know the way mode. And then mix in there is like, and now I'll show you how to do this and that and the other thing. All right, so type in your entries, each coefficient in your system, and then quit out of there, go back into the matrix, go to math, find ref, not ref, but ref, select the matrix that you just put all that information into, which is matrix A. You get all that stuff, which is fun to look at, I suppose, but math, enter, enter, so that you can have the cleaner variation of it. All right, so the interpretation of this is going to be the important piece.
Fuzzy.
Yo,
How did you do the matrix with calculator?
it really just hurt my neck doing that. Sorry. How did I
Yeah, get to the matrix, like the second matrix.
second the inverse key, which is matrix? God. Spontaneous reaction I'm going to pay the price for the next 7 to 10 days.
That, you know, that reminds me. What? The Game Boys. Yeah. The old version, you had the.
This thing, over both yours, I dropped down the staircase.
Drop myself down the staircase. Twice in 2 days. Like, I don't recommend it. So. The worst is on the second day when you're at the top of the steps and you're thinking, glad I got that out of my system. No way that's going to happen 2 days in a row. Boom. Not good. Not good. So, anyway, the coefficients here correspond to the coefficients in the original equation. So, let's go back to that. And there we are. So now it's a matter of just kind of taking this information and having it correspond to something more meaningful, right? So if we started off with 2x plus 1y plus 1z equals 1, and that simplified itself down to 1x. I'm going to write it below. This is really 1x plus 0y plus 6/13 z equals 9/13. Then we have 0x plus 1y plus 1/13 z is equal to negative 5/13. All right? Which doesn't look like a parametric equation at all. It's definitely not a vector value function, so now what? Right, so here's the thing. What I want to do is I want to rewrite each of these equations so that they're solved for one variable in terms of some other variable. It looks like it's going to be very easy to solve for x in terms of z, and in the first equation, and solve for y in terms of z in the second equation. So I'm looking at x equals 9/13 minus 6/13 z, and I would also have y equals negative 5/13 plus 1/13 z. All right. Now, minus.
1/13.
All right. So then the question would be, okay, well, what's z equal to? Well, it can't be equal to nothing, right? It's got to be equal to something. Is it equal to something in particular? Maybe. But there's no indication that it's equal to something in particular. So really, since x is dependent on z and so is y, it's not bounded in any way. We don't have any restrictions on z. So therefore, z would be some value z.
There's an algebra and calculus now about finally overlapping.
So it looks like it's what we would call a free variable, right?
Exactamundo. So that's exactly what it would be. It's a free variable because it could be anything. Its domain is unrestricted. All right. So how do we redefine this? Well, we could leave it like this, I suppose. But if we're thinking about parametrics, we generally define parametrics in terms of t. So t represents time in most cases, but just last class we let our parameter equal s. We've let parameters equal theta before. We could let a parameter equal z, but if we want it to be some completely unknown quantity, what I could do is let z equal our parameter t, in which case we would have x equal 9/13 minus 6/13 t, y would be equal to negative 5/13 minus 1/13 t, and z would be equal to t. Now, does z have to be equal to t specifically? Well, I don't know. It could be anything. Well, the issue is we don't have any context here. So t, since it represents time in most cases, the flow of time is different in particular situations. I mean, you could even think of time moving at different rates, but you could also think about just simply the units of time. If it's hours versus minutes, it could be apples and oranges depending on how you define things. So at this point, we would just say z equals t, but maybe you want to clean things up. Maybe you want z to equal 13t. If that's the case, then these guys would clean up a little bit. There's no restriction in what you can let your value of t be equal to.
I was about to say, is it wrong to think of it because it's two planes intersecting? They're kind of like just functions of z, different x values and different y values for every z. Like it's a line, and z is going off in different directions. Like,
Right. Yeah. So exactly. So you're going to have differing x and y values depending on what your value of z is. So at different levels, different heights, you're going to have different values of x and y. So whatever you define your z value as is going to be sufficient as long as it supports the idea that it represents a height at some point along the curve. In this case, it's going to be a linear relationship, but it could be a curve. So in vector valued form, we would say 9/13 minus 6/13 t, negative 5/13 minus 1/13 t, comma, t. Right. Now, do we have to write it as a vector value function? No, not necessarily. You've satisfied the requirements of the problem by writing it in this form. This is how we write parametric equations. Just now we're moving towards writing them in vector form, but there was, unless I forgot, which can happen, said find the intersection of the planes. It didn't say to represent your answer in any particular form.
I was going to say, is there something like that in Geogebra where you can draw the two planes and then draw that line?
Funny you should mention that. So looking at Geogebra,
It's interesting. I can already imagine how it looks.
so let me get my two original planes in. I'm gonna. Oh, one of them is a holdover, so I can keep that one. The other one was 3x.
3x minus 5y plus z is equal to 4.
All right. So that's the intersection of planes, and you can see there is a path there, and that path would be a linear function. So a way to handle that would be to say intersect. Intersect, not intersection, between D and F. There it is. Right. So this doesn't look anything like what we just came up with, but that's not a problem because this is a Lagrange. We'll get to that. And it seems like I'm trying to impress people now, but we're going to learn about Lagrange multipliers later in the unit. But this is along those lines, so it's not a parameterized relationship, but it plotted it correctly. That definitely looks like the path that we had in mind. So let's see if our equation is going to stand up to this. Curve. We have
9 over 13.
9 over 13.
Minus 6 over 13 times t.
Minus 6 over 13. I'm going to use that multiplication, so then we'll just play it safe, times t.
Negative 5 over 13 minus t over 13 or 1 over 13. Doesn't matter.
T over 13 sounds good to me.
And then t is the...
And then we can give it some width, so I'll go negative 10 to 10. If it's not good enough, I'll adjust it.
Oh, wow.
All right, so...
Wait, why'd you have to do 10 to 10?
Just to give it some domain. because if I don't, then it's not going to know where to start and stop it. All right, so, well, the path was there before. Let's get rid of that. You can still see that there's still a path there. Let me get rid of this one. Oh,
It's not the same thing.
it's not. Did I type it in wrong?
Sorry, it's not minus 1 over 13?
Oh, minus 1 over 13. Oh, wait, minus 1 over 13t, though. No, that's
Which is
fine.
the same thing.
Yeah, what did I screw up?
Those are all the same values.
Those are
Or did we do it wrong?
pos. Double checking. Double checking. 5, 1, negative 4. You know what's concerning though is that I don't see a z equals here, so I'm wondering that happened here. You see, I have a z equals.
Can you put another P up there?
I thought I did. It's right there.
You need your Z term, maybe.
Or should we have left it as
Do you define? Are you defining and giving it a Z term for the same one? So I'm supposed to define T for the whole.
Oh, thank you.
Yeah.
Thank you. I need another. Yeah.
Why do you need another
Because you're defining T.
Yeah, because t for the z term and then t to say that this is my variable.
Right.
Ay, ay, ay.
Oh, there it is.
Yeah.
that's the
Oh,
other one.
hold on. There it is.
There we go. See?
Okay.
It's there now.
Defining your-
Yeah, I just left it. Okay, so, well,
Right.
it's important that the math was right. So that's good, but that was a red flag. If you, I mean, you're supposed to have 3 variables, so if you don't, then that's an issue. All right, so that's good news. Anyway.
It's really cool.
All right, so the last thing that we're going to cover tonight is the distance between a point and a plane, which I should zoom in on for you. Oh, not reset. That's not what I want. All right, so find the distance between a point and a plane. So we have some point x1, y1, z1 in a plane that contains x sub o, y sub o, z sub o, and that's normal vector n. Compute the projection of the displacement vector from P to Q onto vector n. All right, so this is really just kind of the nuts and bolts of it. You have the plane equation. So here it's written as ax plus by plus cz plus d equals 0, because since d is some arbitrary constant, d could take on a positive or negative value. So whether it's equal to positive d on the right or a positive d on the left, it doesn't make a difference. And you have a normal vector that's a, b, and c. The displacement vector is it's just the subtraction of the different components. All right, so from the component form of qp upon n, right? So qp as a projection in the direction of n, right? So I'll just do a little hand waving here rather than going through the entire proof because time. I'll start off next class with the proof and we'll go from there, but I'll just give you the general idea here. I'm looking for the distance between point P and the given plane, all right? So I'm just gonna highlight that real quick. That's this guy over here. All right, now my normal vector could be pinned at any point on the plane, right? It may not be anywhere near the point on the plane that's closest to the point in space. If that's the case, you might say that, well, what's the point of having that piece of information, right? The idea is that if I can take this line, which would be a particular vector, and project it onto vector n, which is that normal vector, all right? So this would be the projection. Upon n of qp. If I can take the component of that, so the projection would be really the amount of this vector that's acting in the direction of that. So if I were to take just, just kind of the imaginary piece of this vector, the part of it, just the ethereal part of it that's acting only in the direction of n, and just kind of grab it and push it in the direction of n, that would be the projection upon n. If I could find the value of that, that would be the component that of QP that's acting in the direction of n. Right? So why would that be meaningful? Well, that would give us a length. That length, this length over here, might not seem meaningful until you realize opposite sides of a parallelogram are congruent. So if I know this length here, then I know this length here. And that's the one I need. So if I can find the component of QP acting in the direction of n, then I will have the distance between P and the plane, the shortest distance between P and the plane. So that's the conceptual piece. I'll get into the proof next class. But that leads us to this idea, the component of QP in the direction of n, all right? Which in turn simplifies to this formula, right? And that's where the proof will come into play, because we went over how to derive the component form of a vector last unit, but it's not fresh. So I'm going to take you through it from top to bottom next class. All right? But the good news is it's pretty procedural once you have this relationship. All right? QP dotted with n over the magnitude of n. All right? So n is our normal vector related to the plane. So n in this case would be 1, 1, 1. All right? We have a point P. This is a point in space. The one thing I seem to be missing is a point Q. All right? Now, something I alluded to is the fact that I don't really care what Q is. As long as it's a point on a plane. So Q must be a point on the plane. I don't care where it is, though, which is great news. Wonderful. I mean, it's the best possible news. What that means is if I can come up with an x, y, and z value that satisfies this equation, I'm good. And anything will do. So Q, all right, I'm going to let it be 1, 1, and whatever z has to be in order to equal 4. So 1 plus 1 plus meh equals 4. Meh would be 2. All right. You might say, all right, I want to go even simpler. 0, 0, and then what? 4. Right? Anything that satisfies this equation would necessarily be a point on that plane. All right? If you want something bigger than 4, maybe you were like, okay, well, I'll call your bluff. 10 and 10. So 20 has to be negative 16. All right? Also a point on the plane. Any values that you plug in here for x, y, and z that satisfy this equation will be a point on the plane. So really, you can't go wrong with that. Right? The only way you can go wrong, I suppose, would be if you didn't know to look for a point Q. Because you might look at a problem like this on a test and say, you didn't give us enough information, how am I supposed to do it? Right? When you realize, well, you had enough information all along. Right? So that could be kind of frustrating. So anyway, Q to P. And I'll write P right next to it, just so I can point at stuff. So 3 minus 1, 1 minus 1, 4 minus 2. So I guess I'm not really pointing at anything. 3 minus 1 is 2. 1 minus 1, 0. 4 minus 2 is a 2. 202. All right, so that's my QP. I need to dot that with n. It's really kind of, if you like math, it's kind of cool, this particular topic, because I'm going to show you, you remember optimization from Calc 1, finding maxes and mins. I'm going to show you optimization in 3 dimensions, in 3 space. That'll also help you find the distance between a point and a plane. And it'll give you obviously the exact same answer, but in a completely different way. And like I said, if you like math, you'll look at that and say, oh, this is cool stuff, you know. I think this is the probably the cool math course. I mean, forget about grades and stuff because like that makes everything not cool. But like the material itself is stuff that's cool. It's interesting in a pure math sense. And I get on my soapbox and I forget what I'm doing. All right, so I think I did it right. So 4, hopefully. Now the magnitude of n is what I need. And I mean, that probably couldn't get any easier, unless it was all zeros, I guess. So root of 3. So the distance would be the quotient of the dot product of QP and N. Now, it's an absolute value symbol over that. I mean, absolute value often means magnitude, but sometimes it actually just means absolute value. What it's telling us in this case is if we got a negative number, drop the negative. All right. So in this case, it was positive, so we're good. So 4 over root 3. And radicals on the bottom of fractions, because I know somebody, I forget who it was, it wasn't a bad question during the test, asked if you needed to rationalize stuff like that. You know, even if I required you to, I'd forget to take off anyway, so don't worry about it. Question?
Professor, for Q, where did you get the 2? It's 1, 1.
This 2?
Yeah.
I assumed 1 and 1, so if I plug a 1 and 1 here, the only value that would satisfy this equation would be a 2.
Oh, okay.
So whatever you decide on for x and y, you have like in statistics we'd call that degrees of freedom. You have 2 degrees of freedom in a 3 variable system. You have freedom to choose 2 of the 3 variables. The last variable is automatically determined based on the structure of the equation. All right. So, like I said, if you wanted x and y to be 0, then z would have to be 4. All right. So the math takes over once you decide on your first 2 variables. All right. Now, number 11, I'm going to put a star on, and that's where we're going to end class, just to give you a little bit of a taste of what you're expected to do there, because it just seems like, yeah, I'm doing all the easy ones here. What's the deal here? I'm actually leaving a pretty manageable one for you. You see here they give you 2 planes. You know what to do if you have a point and a plane, right? When they give you 2 planes, you can still make it a case where it's a point and a plane. Because if you choose a single point on one plane, and you're looking for the shortest distance between that and the other plane, okay, cool, you do that for 1 point, you do the same thing for 10 other points, it's going to be the same distance, because they're parallel to one another, all right? So in your first equation, come up with a point that satisfies this equation, all right? So guess an x and a y and come up with the corresponding value of z. That'll be the point, like in number 10, and then work off of the other plane. All right, so you come up with the point for the first plane, and then you get to work on the problem just like it was question number 10. All right, so